Hello everyone, welcome back to Turning Turing. In today's video, we'll explore quicksort, one of the fastest and most widely used sorting algorithms. We'll break it down step by step, dry run an example, write C++ code, and analyze its efficiency. So let's jump right in. Quicksort uses the divide and conquer strategy to sort an array efficiently. Here's how it works. The first step of quicksort is to pick a pivot. So we choose an element from the array randomly. Commonly, the pivot is usually the last, first, or the middle element of the array. The next step is partition the array. So we divide the array into two halves around the pivot. So all the elements which are smaller than the pivot goes on the left side of the pivot element, and all the elements which are larger than the pivot goes on the right side of the pivot. And that's how you partition the array into two parts, one smaller than the pivot, other larger than the pivot. Then we recursively apply sorting on both the parts separately. So by breaking the array into smaller parts around the pivot, quicksort sorts the entire array efficiently. And since we are breaking the array into two parts at every step, we call it a divide and conquer strategy. Let's try to dry run this algorithm on an example. So let's take an example array 8, 3, 6, 2, 7. And for this particular example, we are going to choose the last element as the pivot at every step. So at the first step, our pivot will be 7. So we'll divide the array into two parts where all the elements less than 7 are on the left side and all the elements greater than 7 are on the right side. So when we do that, we will have 3, 6, 2, 7, because all the elements which are smaller than 7 on the left side, and all the elements greater than 7 on the right side. So here we'll have 8. Now we have actually divided the array into two parts. So one part is A1, elements smaller than the pivot. Second part is A2, elements greater than the pivot. So now we'll recursively apply quicksort to both these parts. So let's say here we have A1, which is 3, 6, 2, and here we have 8. So as we know that any array of size 1 is sorted by default. So we would not apply any recursive sorting on this particular array because this is already sorted. Now we'll apply quicksort on this particular array A1. So again for A1, we'll select the last element as the pivot. So here 2 will be the pivot element. Now in this step again, we'll divide the array into two parts with all the smaller elements less than 2 on the left hand side of 2 and all the elements greater than 2 on the right side. So in this particular step, we do not have any element which is less than 2. So there's nothing. Then we have the pivot element, and then we have all the elements greater than 2. So again here we would have divided the array into two parts, A3 and A4, but A3 is a null subarray here, or a 0 element subarray, because there's no element smaller than 2. So here we'll only apply quicksort recursively to A4. We have 3, 6 here. Now again we'll select the last element as the pivot, which is 6. So elements smaller than the 6 are going to be on the left side and elements greater would be on the right side. So we'll have 3. Then we have the pivot element, and then we have nothing greater than 6. So this is the subarray here, and we do not have the second subarray because there's no element in the second subarray. We apply recursive quicksort to this subarray. Now we know that by default any array of size 1 is already sorted, so we do not apply any recursive sorting to this. So we just move up. So here the array that we have got is 3, 6. We'll replace this array here. So this will be 2, 3, 6. Now this will be replaced here. So A1 after sorting looks something like 2, 3, 6. Then we have the pivot element, and 8 was already sorted. So finally our entire array is sorted. So let's quickly go through the code for quicksort. So this is our main method where we are applying quicksort. So the first step is finding the pivot element and sorting the array around the pivot element. So in this particular step, we find the pivot element, and anything smaller than the pivot element goes on the left of the pivot, and anything greater than the pivot element goes on the right of the pivot. So once we have done that, we'll have the exact index where the pivot will come. So let's say ABC was the array, we picked C as the pivot, and A was less than C and B was greater than C. So after this step, our array would look something like this. So now we'll have the index for the pivot in this sorted step, and the pivot index is 1. So this pivot index will be returned from this method. So pivot index here will be 1. Now we have to apply quicksort to the two parts or the two subarrays on both the sides of the pivot. So we'll apply quicksort on the left side and we'll apply quicksort on the right side. So left subarray will be from start of the array to pivot index -1, and the right will be pivot index +1 to end of the array. And we'll recursively apply quicksort to these two parts. So that's what we have done. We've applied quicksort to the left part, which is from start to pivot index -1, and we've recursively applied quicksort to the right part from pivot index to the end. We could have done pivot index +1 also here. So now let's go through the method which actually finds the pivot index and divides the array into two halves and sorts the array around the pivot. So in this particular algorithm, instead of choosing the last element as the pivot, at every step we are choosing the middle element as the pivot. So we have the start of the array, end of the array, then we pick the middle element as the pivot. Now this particular while loop is dividing the array into two halves. So everything which is smaller than the pivot is going on the left side, and everything greater than the pivot is going on the right side of the array. So once we are done, at the end of this loop, the index I or the value in I will be representing the index of the pivot in this sorted array. So what we are doing in this loop is actually in the first step we are trying to find the index which is on the left hand side of the pivot, but the element there is greater than the pivot, and on the right hand side we are trying to find an index where the element is smaller than the pivot element. If we have found both these, we'll just replace these two, because the right side one should actually come on the left and the left side one should come on the right. And while doing this, if at any time I and j have crossed, that implies that all the elements are on their correct side. So we do not have to do any swaps. So if you want, you can further go deep into this particular while loop by taking an example. But in case if you face any doubts, feel free to write in the comment section below and I can give an explanation there. So now let's discuss the time complexity for quicksort. So in the case where at every step we are able to divide our arrays into exactly half, so that is going to be the best case. So what happens here is, let's say that we have A, B, C, D, E. So in the first step, let's say that we selected E as the pivot element. Now we have divided the array into two halves. Let's say A, B are on the left, then we have the pivot element, and C, D is on the right. So let's say after this, our arrays got divided into A comma B, then they got divided into C comma D. Now obviously in the next step we are only going to get a one size array. So in this particular case, we are always dividing the arrays into half. So the height of this particular tree is going to be log n, because we know that at every step we are dividing it into half. So let's say that the initial size was n, that at this particular point we'll have sizes n by 2 and n by 2. Here we'll have sizes n by 4 and n by 4, and this will go on till the time that n by 2 raised to power h is equal to 1. So height is going to be log n. So the height of this tree is going to be log n. So the time complexity here is going to be big of n log n, because at every step we are parsing the entire array once. So here we'll be parsing the entire array, that will take n time. Here we will be parsing entire array separately. So this is going to take n by 2 time, n by 2 time. So total at this step also we'll have n. So the total time complexity is going to be n into height of the tree, which is log n. So this is going to be the best case time complexity. Now let's discuss what is going to be the worst case time complexity. So let's take A, B, C, D, E, F. So the worst case time complexity is going to be in the case when you are dividing the arrays unequally, when you're distributing it around the pivot and the distribution is very unequal. So your one side is very big as compared to the other side. So if that is going to be the case, then the height of the tree is going to get longer, and that's why the total time complexity is going to increase. Let's see how that. Let's say at this step we select F, and after sorting, F is actually the last element. So all the elements are smaller than F. In that particular case, this is going to be one subarray and this is going to be the other subarray which is empty. So now again we'll apply quicksort to this step. Now let's say in this step we again pick E as the pivot and all the elements are smaller than E. So in this particular case, A, B, C, D will be there. We'll have pivot E and the other subarray is going to be empty. So now we'll apply quicksort to this particular subarray. So let's say at every step we are picking the pivot which is greatest element and all the elements are coming on one side, either left or right. So if that is the case, the total height of the tree will become n, and at every step you are parsing almost the entire array. So that is at every step you are making n operations and the total height is n. So the worst case complexity will be big O of n square. So the time complexity for quicksort depends on how you're selecting the pivot. If your algorithm for selecting the pivot is optimized, then your time complexity is n log n. But if you're selecting the pivot in an unoptimized manner, your heuristic is not right for selecting the pivot, then you'll have the worst case time complexity as big O of n square. Now coming to the space complexity. So space complexity is big O of 1. We are not using any helper array. We are sorting in place in the same array. So the space complexity is big O of 1 and it's an in-place algorithm. It does not require any extra space. So for large data sets, you'll be saving a lot of space. And quicksort is actually used in a lot of real world applications due to its speed. Even the library methods have a combination of quicksort, insertion sort and all. We've already discussed that. Now cons, obviously, if your heuristic is really bad, then your worst case time complexity goes to big O of n square, and it's not a stable algorithm. That is, the elements which are equal, they do not maintain their original relative ordering. And that's quicksort for you, fast, efficient and widely used. If you found this video helpful, hit the like button and subscribe for more programming content. If you have got any doubts, questions or suggestions, please use the comment box to drop your query and I'll try to answer it there. Thanks for watching. See you in the next video. Till then, keep safe and keep learning.